incredible ideas and breakthrough that will emerge from this extraordinary event. Let's make history together. Thank you very much.
And students from around the world. I see here we have 12 countries in this conference. I have here Malaysia, Guam, Thailand, Nepal, Taiwan, Indonesia, Mongolia, Iran, Philippines, Mexico, Bosnia, and Italy. 12 countries. This is really great to have you all here from all over the world, some from very far. Thank you so much for your effort to come here and join this event. Let me refresh you with the aim of this conference. The aim of this conference is to foster science among secondary school students through scientific projects in 5 categories. They are mathematics, physical sciences, computer science, environmental science, and life sciences. I would like to thank our keynote speaker, Professor Kwek Leong Chuan from Singapore, and all the experts from the university in Malaysia and also the steering committee members who has taken time out of their really busy schedules to share their knowledge with us. Your presence makes this event truly special. Thank you very much. Again, I would like to introduce you to the steering committee members. Please stand up and show your face to everyone. First, from Singapore, Professor Kwek Leong Chuan. Professor Wangli Mustafa from Malaysia. Mr. Sanjay Karamari from Malaysia. Professor Chow Ming Fu from Taiwan. And Mr. Shailendra Harha from Indonesia. There's still some missing here, the steering committee members. Is our Dr. Roberto Hidalgo from Mexico, Sri Satyawati Saiful from Indonesia, Dr. Vasily Pavlov from Russia, and Mr. Anu Sinha from India. I also welcome Professor Rameshwar Adhikari from Nepal. Are you here? Not yet, but he's here, yeah? He will join us later. Dear participants, I encourage you to take full advantage of the networking opportunities and engage with each other in the poster session. This is a great platform to share experiences and build meaningful connections. Let's make this conference a memorable one by engaging, learning, and inspiring each other. Together, we are not just attending a conference, we are building the better future which will be led by these young scientists. On this occasion, I would like to thank the organizing committee, Malaysia Young Scientists Organization, led by Mr. Razmi. Thank you so much for all the hard work in preparing this event. Again, to all participants, thank you once again for joining us. I wish you all a great day ahead and hope you have a great and enriching experience in APSIS 2034. Thank you very much.
Yeah, it's cost center system multiple attention to introduce the science around our research with monitoring
which emits ultrasonic rays calculating the distance between the device itself and the water tank. And the water surface. The blinking and the LCD
I spent the week okay, I'll share this.
Actions to have the environment without spending much money or time.
Yeah.
on your measurements. Okay, so that's very important. Now we do a third thing. What do you see? Another example. Do you see a guy looking at you? Or do you see a guy looking to the right? Yes, some of you say you see both. But it really depends on what you measure. Again, the measurement is all the height. Measurements, but the thing is that when you do a measurement and settle on it, very often you are fixed on that picture. So measurement destroys this superposition. So when you see two things at the same time, we say that that is a superposed state. I'll not go into this one because Trump is having the election now. So I'm going to play a video by Akira Tanomura, who unfortunately passed away by now nearly more than 10 years ago. Akira was a very good friend, and what he did was that he invented what's called electron holography. Some of you may have heard about holography using light. So you can, with holography, you can create three-dimensional images. And then you can look at it from different angles and still see different sides of the image. Akira, what he did was to do it with electrons. So this is the experiment he's going to talk about. And so now I like to play this video many times. Oh, you can't hear it. So instead of Akira's voice, let me read what he has stated. So Akira was actually presenting this during the Faraday's lecture. He could have got his Nobel Prize for electron holography, but he passed away before that. Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons, so individual particles. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in a microscope is very small, not to mention the chance of finding two. And since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the double slit biprism, thus creating a uniform distribution without any interference when accumulated. So you should see uniform distribution. Under such conditions, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference pattern. And since this experiment lasts more than 30 minutes, I sped the movie up. Now interference fringes are clearly visible. So that's what Akira said. So you can see, if you see, maybe you can't see it from far, you will see black lines. Thank you. Oh, this is Akira, okay, back in 2012, more than 10 years ago. So, in the lab, we are now able to build what's called nanowire, these hairline structures. The hairs are not always very long. Some of them are very short. Okay, but these are hairline structures. The other hairline structures you can do is carbon nanotubes. But these are just nanotubes formed from perhaps gallium arsenide. So you can manufacture such nanowires. And now suppose you dope these nanowires with another material. So simply gallium with arsenide or indium with phosphate. Then you find that you have a free electron that's created. Of course, you don't create just one free electron. Typically, you create thousands of free electrons. But this wire is so long, 1 centimeter long. So, and the electrons are so tiny. So even if you have 1,000, it is very sparse, sparsely populated. So you try to locate the position of the electron. Sometimes it's here, sometimes it's here, sometimes it's here, sometimes it's here, sometimes it's here. So you keep locating the position of the particles. After many of these measurements, you get an intensity pattern that looks like this. When you put them together, it is your dark and bright fringe that Akira Konomura was talking about. But at the lowest possible temperature, you find that this end is dark, and so is the other end. So you can use a computer and plot the intensity pattern. You will see this is dark, and also that is dark. You can raise the temperature ever slightly. If you raise the temperature, then you find other patterns start to emerge. In particular, at the next higher temperature, you see two bands characterized by the two bright intensity. And of course, the dark spaces remain dark. And if you do more, higher temperature, you see 3 bands. If you do higher temperature, you get 4 bands. Eventually, you get many bands. So, what is the nutshell? And on top of that, you can, like the young lady and the old lady, you can allow a certain percentage of the particles to have the lowest possible temperature, lowest possible energy, and some proportion to have higher temperature. So you have a mixture. So sometimes when you measure, you end up with the pictures of the lowest single band. Sometimes you end up with 2 bands. And when that happens, you get a different pattern, like that. This is a superposed pattern. Do you see the single band? Do you see the double band? It's a mixture of both. Now, this brings me to a research. Whenever in research, you see 2 curves, one obeying seemingly one half of the curve, and another aspect behaving like another